Shenken. How do I pronounce your name? I'm sorry.
Oleg
I'm
Shekin. Yes.
Shekin. Okay, thank you very much. Will give us a presentation now on VCSEL-based power efficient scale-up interconnects.
Thank you very much for the opportunity to speak at this forum about VCSEL-based high-density optical interconnects. You can go to the next slide, which just describes why we're here. With the amount of compute that is necessary, more hardware is becoming often not the answer. We need innovation, and that's why we have this forum to break some of these barriers that are emerging. Go to the next slide. Here in a data center, a number of distinct communication networks, optics is already prevalent in the data center interconnect front end and also the scale out. Scale up is, which is the focus of the work we're presenting here, is connected predominantly electrically. And this is the layer of significant expansion. More GPUs are being connected, and with each generation, the total bandwidth per GPU or TPU is doubling, but also the scale-up domain is growing. And with that, there are requirements for space, connectivity, and also power. And if you go to the next slide, in the table here, this is an example of generations from NVIDIA. Google does a very good job documenting their releases, and you can also look how on their references on how the total bandwidth, but also scale-up size are increasing. So there is a need for optics and optical interconnect that also allows that is scalable in the amount of bandwidth, that is future-proof, to connect more GPUs, more connections per network over longer distances, and also with less power. And in this presentation, if you go to the next slide, I'll introduce certain data. It's not a complete picture, but I would like to show you that VCSELs and VCSEL-based interconnects are very competitive and in often a technology with advantages over other technologies that are being evaluated in this field. VCSELs are a very high volume technology. They can bring bandwidth, that also high density, can be power efficient, and also have a great reliability. Go to the next slide. VCSELs were introduced in the 90s in the datacom and very familiar to this community. Over the last 10 years, VCSEL technology has undergone a significant transformation, in part, significantly due to it being deployed in consumer 3D sensing applications, but also in automotive applications. And 3D sensing introduction about 10 years ago developed ability to provide volumes, and also the industry developed a ramp capability. And that would also strengthen the supply chains, but also everything that would come at VCSEL factories that needed to be done at volume, from epitaxy to wafer fab to testing to reliability. Automotive brought focus on reliability. As anyone who worked in automotive field, reliability in automotive, because of strict safety standards, is front and center. And Lumentum participated in all of this development, and in 2025, we propose to use technology that's based on all of this latest development for datacom applications, for high density interconnect. Go to the next slide to introduce just the performance level. What you might have seen on the previous slide is that the operating wavelength for the technology we're proposing is 1060 nanometers. On the left, you can see here LAVs of lasers, and there's plenty of power at all temperatures. On the right, this is an example of one of the cells of the accelerated testing we're performing. Usually when you look at a VCSEL specification sheet, its performance is spec'd at 6 or 7 milliamps. Here you can see a device that's operated at a current of 8 milliamps, which is over usual target operating condition, but also the junction temperature of 181 degrees C and over 5,000 hours. And this group of devices, you can see there's no failures. And this is one of the subset cells from a much broader multi-lot accelerated study which we conducted, and which also did not have any failures. So this is an example of the kind of transformation and changes that VCSEL technology underwent in recent years. Go to the next slide. Now this introduces the architecture of VCSEL array for high-density interconnect. As you can see on this plot, this is a hexagonal array on a silicon submount. And the architecture here is a flip chip. Flip chip is a very scalable architecture because all of the interconnects are done on the bottom through the substrate. So the VCSEL actually emits through the substrates, and that's why 1060 nanometer also helps us here. The backside emission also allows us introduction of optics, which could be shaped on the backside of the semiconductor substrate. And you can see here this hexagonal array. Each of the VCSEL elements has a micro lens on it, and as a result, the output emission is highly collimated and with excellent coupling into fibers. And on the right, you can see here this array lit up. What's also important about 1060 nanometers is that this wavelength allows for a matching flip chip architecture of a photodiode array. So when we develop this link, we have a VCSEL array and a photodiode array. VCSEL is emitting through the bottom, and also photodiode array is bottom illuminated, and they have the same form factor. Go to the next slide. Here you can see the eye of one of these devices at 25C and 85C, and this is 32 gigabit per second, and it's shown here at different currents from 4 milliamp to 9 milliamp. And as I mentioned earlier, often this for very high speeds approaching 64 gigabit per second data rates, VCSEL are spec'd to operate between 6 and 7 milliamps. Now, if you allow VCSELs to go slower, or you do not need to really have that much power in your link, you can turn down the current and go down to, say, 4 milliamp. The VCSEL doesn't need to be outputting all of its power, and that will result further in significant power savings. You can see here on this plot, we have some equalization, some mild equalization on this eye. Now I can tell you we measured around 30 gigabit per second. It was equipment limited in that test, but we measured it that we have beautiful eye down to 4 milliamp without any equalization. So from the point of view of power savings, you can run these devices also at low current and simpler electronics. Now, on the next slide of how this technology could come together to make connections, for example, in a rack. And this is a concept of UCIe-like slow Wi-Fi that's extended using an optical chip with VCSEL and photodiode arrays. Here, schematically, VCSEL arrays are shown as the red dot rectangles with about 19 channels each. This is for UCIES. All you need is 16 data channels. And what we envision is for actually all of the data and sidebands and the clock to go through these data channels. But various practitioners would prefer to reserve extra channels for sidebands or the clock. So in this example here, you could have 16 channels per each of these 8 elements of transmit and receive. And at 50 gigabit per second, you'll be transmitting 6.4 terabit in each direction. Now, if you go into the next slide, you can see how this could look in a rack. Well, if you have 4 TPUs in a tray and you have 4.8 terabits per each TPU, you could now put these 16 channels with any spares that you need into a standard MPU, a 24-channel MPO connector with the standard fibers. And now you can connect it to other trays also, and you can, and each port with this 16 channels would be a 100G port. You can build out for each of these trays. Yeah, you can now have 64 connections, and you can build out with a very high radix GPU networks. And what I want to emphasize here is that this is all of the off-the-shelf componentry that can be deployed already in a network configuration. Some of it could be optimized even further in order to leverage the high-density interconnect with the VCSELs, but VCSELs work very well with what's available.
Okay, Oleg, we're running late.
Okay, very good. This is a similar example of a UACIA chip, now in a similar fashion, moving 32 terabits. And if you can go to the next slide, what VCSELs do very well is that they have high data rates, and also when they turn on, they can switch very efficiently. And high data rates allow keeping these array sizes to manageable levels. And the similar technology as micro LEDs, you can see that the data rates are about 10x, and that goes into 10x fewer channels, and also to almost a 10x, or actually 10x higher terabit per millimeter squared density. Also, in terms of picojoule per bit, VCSELs are very efficient because of this higher data rate. And finally, to close out, this is an example of a switch that we showed at OFC. This is a switch ASIC now connected with a similar UCIES-like arrays that I showed earlier, showing the transmission from the switch ASIC through the VCSEL and into the fibers. And at the end, just a final message that VCSELs are scalable architecture with high bandwidth density and energy efficiency and reliability, and also utilizing existing assembly methods, as well as high volume